Okay, so let's look at what happens to these diagrams. If you remember. In fact, if I have, let's say, this diagram, in the next order, I will get such a diagram also. Even in the next order, I will get this diagram and this diagram and this diagram. In the next order, remember, I have two vertices, two interaction vertices. One is a phi 4, the other one is a phi 4. So this tells me that just contract the phi fields at the point x with each other. This tells me contract two of the fields at the point x with each other, two of the points at the at y with each other, and the remaining two fields at x and y, you contract them with each other. And this is a diagram where you contract each field at the point x with a field at the point y. Of course, they're all higher order terms. And this is, and remember how we write the corresponding mathematical contribution for each diagram. You just multiply them. Each line will be a propagator, each vertex will be some factors of lambda. Just multiply them. So each one of these diagrams, in this case, for example, have the contribution from this diagram as common. What remains will be 1 plus single 8 plus this one plus this one plus higher order terms.
So it's like exponential. It's like exponential.
Well, this is for this basic diagram, if you like. Well, I also have this diagram. This basic diagram at the 0th order. This arrives at the 1st order. This is at the 0th order. Well, I have other contributions. Like this one, plus higher order terms. Basically, I have this one times 1 plus this one plus this one plus this one plus this one plus all the higher order terms.
Because the interaction term is the exponential and this higher order terms.
In the exponent, I have all the higher order terms. If I imagine all possible contractions of my fields or all my diagrams where each leg corresponding to each field is contracted with some other point, I will have all these terms. But you see, this factor and this factor is basically the same. And they all come from, remember, they all come from some contribution from this one. From the expansion of this one. They all come from this expansion. But now let me look at this one. Again, I need to expand. So what is this? Well, there are no external legs. If I consider the Taylor expansion of the exponent, there will be 1 plus I plus ID for x, the interaction Lagrangian, plus I squared over 2 factorial d for x, d for y, time ordered product sorry. Now this is what I have. Well, I can consider these diagrammatically. I have 1 plus. Well, in this one, I have just one interaction vertex. All have to be contracted. In this one, I have 2 interaction vertices, and I have to consider all possible contractions. This is one possibility. This is another possibility. And this is the last possibility. So this sum over here is nothing but this matrix element. I mean, you can work out the overall constants. Including the overall constant, everything is the same. So remember what we are calculating. We are trying to calculate this ratio. In the calculation of the numerator, I have the denominator also. So now I can cancel them. What remains is this matrix element is actually equal to connected to external. Now, I have to calculate all the diagrams that are connected to external legs. I don't need to calculate this one separately, because this part of this diagram is not connected to the external legs or to each other. I need to calculate only this one. Well, this diagram, I still need to calculate. If I want to calculate the 4-point function, I have to calculate that. But if I want to calculate S matrix elements, I don't need that diagram, because that diagram will not contribute to the S matrix. It doesn't describe a scattering process. So I don't have to consider all diagrams. If I want to calculate all the S matrix diagrams, all the diagrams contributing to the S matrix, I have to calculate only the diagrams that are connected, point. For the 4-point endpoint functions, I need to calculate all the diagrams that are connected to the external legs. For the S matrix, the diagram has to be connected. Just being connected to the external legs is not enough. So any questions? So basically now we have our rules. We have described our rules. Draw all connected diagrams contributing to scattering. These diagrams, they should have legs corresponding to the ingoing and outgoing particles, and they can have any number of vertices corresponding to the potential I have. You see here, this is called a vertex. If there is one vertex, it's the first order contribution. If you have two vertices, they are That's the second order contribution. For each line connecting vertices, include a DF. Well, since these are the Feynman rules for S matrix elements, so that's why I emphasize that they should be connecting vertices. Because LSZ reduction formula already tells me that the external lines will be removed in the contribution to this invariant matrix element M. You see here, to calculate this, the LSZ reduction formula basically just removes the propagators corresponding to external legs. Just remove them. Whatever remains is your matrix element M, which you can use to calculate the cross section. And 3 multiply by I lambda for each vertex divide by the symmetry factor. Okay, so what is the symmetry factor? Let's go back to our diagrams. Remember, we calculated these factors. There was for this diagram here, there's a factor 8. Okay, how did I calculate that factor 8? Well, I said that, okay, there's a 1 over lambda 4 factorial from the definition of my potential, from the definition of lambda. Then when I look at all these possible contractions, well, the 4 fields at the vertex, just pick any one of them. That can be contracted with any 3 of them. So you will get 3 identical contributions basically. So you get 3 over 4 factorial, which is 1 over 8. 8 is the symmetry factor for this diagram. What does it have to do with symmetry? Well, you see, look at this part. Just there is a bubble at the top. If you flip that bubble, well, flipping that bubble basically corresponds to contracting field phi 1 with field phi 2, or contracting field phi 2 with field phi 1. Yeah, they are the same thing. So there's that symmetry. Just flipping the upper bubble doesn't change my diagram. Flipping the lower bubble doesn't change my diagram. So there are basically two identical contributions, if you like. Flipping the upper bubble with the lower bubble, that also doesn't change this diagram. So that is an 8-fold symmetry. This shape alone has an 8-fold symmetry. And that is what this 8 is. If you look at this diagram here, you see this bubble over there has a 2-fold symmetry. So you just flip them. That is why you get this factor 2. I personally don't like the symmetry arguments. I prefer to count the factors, like I did over here. I just count them. I find it less error prone. And of course, that symmetry factor argument works only if you get these 4 factorial factors in the definition of your constants. And
change, I mean, if we flip the upper bubble in the upper part, please go on.
yeah, we also have the same
No.
even further.
Yeah, this one, the last one.
Yeah,
Up to down, reverse it up to down.
that's not a symmetry.
Okay, that's not symmetric.
There's no bubble, there's no lower bubble. Only if I flip the upper bubble along the vertical, it has a 2-fold symmetry. Assuming, of course, you draw it symmetrically. Well, there's one more factor which I didn't discuss. Is if we look at all these expansions, there is this 1 over 2 factorial which I didn't talk about. You see, in the exponent, when I expand the exponent, the nth term has a 1 over n factorial. But then, you see, if let's say that this phi 1, I can contract the field in phi 1, let's say, with the first vertex, with the second vertex, with the third vertex, etc. And then I can contract phi 1 with the second vertex, the other field with the first vertex, etc. But this first vertex, second vertex, third vertex is kind of arbitrary. And hence the contribution that I should receive will be the same if I just flip the first vertex and the second vertex. I get exactly the same contribution. That gives me an n factorial possibilities with the same contribution, and hence it will cancel the 1 over n factorial in the nth term. So what you do is I have n vertices. Let's say that I have such a diagram. This is x, this is y, this is z. They are the vertices that I obtain in the expansion of the exponent. In principle, I also have such a diagram. This is y, this is x. Well, let me just remove the z. There is also this contribution. But these two contributions are the same. So I just calculate one of them and multiply by 2 factorial. Well, in the second order in the exponent, I also had 1 over 2 factorial, so they cancel. The only thing that remains is the so-called symmetry factor. So in fact, I can straight away write the contribution of this diagram to my S matrix. What I need to do is dx, the Feynman propagator between x and y, another Feynman propagator between x and y, just integrate over x and integrate over y, and I also have I lambda squared, symmetry factor is 2.
Sorry, you've identified, this is not symmetry factor argument.
This is the symmetry factor argument.
Okay, it's the same. Okay.
For this diagram, the symmetry factor is 2.
Right. But for 3 vertices, we would have 3 factorial?
For if you have phi cubed, I would divide it by 3 factorial. Yeah.
Oh, n factorial.
So any questions in these diagrams? Well, you see, now we don't do all the commutations, all the integrations, etc. What we do is we have the building blocks of our theory. In the phi-4 theory, the building blocks are this vertex, and basically that's it. You have your incoming particles, you have your outgoing particles. Here we have a black box. And fill that black box with your building blocks. Okay, there is the vertex, and there is also these lines connecting the vertices. Just identify any diagram that you can think of. If you are interested in the first order in potential, then you have a single vertex. If you are interested in the second order, you have 2 vertices. Just make sure that you connect each line to some external leg eventually. You only need to draw the connected diagrams if you would like to calculate the S matrix element. And so for such a diagram, for example, the corresponding contribution to your invariant matrix element will be given by that expression. Once you identify your diagram, it's straight away to write the corresponding contribution. And once you identify your invariant matrix element, well, we had already discussed how you can write down the corresponding scattering cross-section. So any questions on how to do these?
Is the symmetric factor coming from the, I mean, we have one vertex, and there are 4 legs of it.
Mm-hmm.
And if we name those legs, there are combination then. I mean, 1, 2, 3, 1, 2, 2, 1, 2, 4, etc. We didn't calculate them directly in our calculations, as far as I remember.
We did. You see. Why did we introduce this 1/4 factorial?
Yeah, I mean,
Well, basically, if we are connecting our vertex, the lines connected to our vertex with with other fields, well, you have 4 factorial different ways of connecting them.
yeah,
So that 4 factorial ways is cancelled with this 1/4
that's the
factorial.
symmetric factor, right?
No, that's not the symmetry factor. So this doesn't have any symmetry,
Mhm.
assuming this doesn't have any symmetry at least. Now, if I connect my vertex with itself,
Mhm.
not all of these 4 factorial ways will be present.
Yeah,
There will be less possible ways of contracting them.
because of we can connect from other points.
Well, you see, let us calculate the symmetry factor over here for this diagram. You see, here the symmetry factor is not because I am connecting the field at a given point with another field at the same point. Here, I don't have such connections.
Such a connection.
I connect fields at different vertices, but still there is the symmetry factor. Why? Let's see. Here I have two diagrams, 2 second order. So in the interaction vertex, I have 1/4 factorial, 1/4 factorial. Now this line over here can be connected to 4 fields at the point x.
Yeah.
The other line can be connected to the remaining 3 fields. Well, the same thing will happen over here. This line can be connected to 3 fields at the point y, no, 4 fields at the point y. The other line can be connected to any one of the 3 remaining fields at the point y. So after I have all these contractions, at the point x I have 3 fields left, at the point y I have 2 fields left. I can let me pick up any one of the fields at the point x. It can be connected to any of the 2 fields remaining at the point y. And the remaining fields, they have to be contracted with each other. So that's all. So this is 1/2. So I kind of find it confusing to calculate these symmetry factors. I'd end up missing some factors sometimes in more complicated diagrams, not in these ones, but just counting them makes more sense to me. And furthermore, for example, when we will be eventually studying the standard model, probably next term in QFT2 or other theories with complex fields, with spinor fields, etc., in those theories, these symmetry factors almost always turn out to be 1. So I don't need to worry about these symmetry factors anyway.
Is there such a beautiful world?
In practice, in research, you just always use FineCalc or like a computer for this, or do you actually, does anyone still count these by hand?
You see, in standard model, in the computations I have, these are just 1. They don't exist. Well, do you mean in your work, when you do your own computation? Well, I use computer programs. In my work, what my students does, they do by hand. At least once. So you see, let's look at this one. I have these propagators connecting different points. And remember what this Feynman propagator is. It's d4k, e to power I k x minus y, and I over k squared minus m squared plus I epsilon. And by the way, this is equal to d4k, e to power minus I k x minus y, I over k squared minus m squared plus I epsilon. I can just change my dummy variables k to minus k. The denominator doesn't change, the exponent changes sign. So this is df y minus x. At least this is a property of the scalar theory. This is not in general true, but at least in the scalar, real scalar field, this is valid. Well, let me calculate this one. Let me also add the external fields, the external legs. You see, this is the contribution to the S matrix, but to the n-point function, to the 4-point function, I will have the f x1 minus x, the f x2 minus x, the f y minus x3, the f y minus x4. Let me write the Fourier transform. How many propagators I have? 1, 2, 3, 4, 5, 6 of them. I have I over ki squared minus m squared plus I epsilon squared, all 6 of them. Then I have d4x, d4y. Then I have the exponents. Minus I k1 x1 minus x minus I k2 x2 minus x minus I k3 x minus y minus I k4 y minus x minus I k5 y minus x3 minus I k6 y minus x4. Well, the x and y integrals are trivial. No, so there is no square over here. Each one of them will bring me a Dirac delta, 2 pi to the 4. The x integral will bring me a Dirac delta k1 plus k2 minus k3 plus k4. And the y integral will bring me I have k3 minus k4 minus k5 minus k6. And then what remains is the exponent minus I k1 x1 minus I k2 x2 plus I k5 x3 plus I k6 x4. This is what is left. Well, remember the LSZ reduction formula. LSZ reduction formula will tell me to take the derivative with respect to x1, the act on x1 with the Laplacian, etc. Basically, it will bring me a k1 squared minus m squared term from this exponent. But here I also have a k1 squared minus m squared term. So LSZ reduction formula will eventually tell me just to get rid of the legs connected to the external lines when I act on this expression. But let me keep that for the time being. So I have one to d4 k1 divided by 2 pi to the 4 e to power I k1 x1 divided by k1 squared minus m squared plus ai epsilon d4 k2 divided by 2 pi to the 4 e to power I k2 x2 divided by k2 squared minus m squared plus I epsilon. And I have d4k k5 to the 4 e to the power I k5 x3 divided by k5 squared minus m squared plus I epsilon d4 k6 e to the power I k6 x4 divided by 2 pi to the 4 k6 squared minus m squared plus I epsilon. Remember, all these factors will be eliminated by the LSZ reduction formula. Now, what remains is d4 k3 and d4 k4. And 1 over k3 squared minus m squared plus I epsilon, 1 over k4 squared minus m squared plus I epsilon, 2 pi to the 4, Dirac delta to the 4, k1 plus k2 minus k3 plus k4, 2 pi to the 4, Dirac delta to the 4, k3 minus k4 minus k5 minus k6. And remember, in this notation at least, k5 and k6 are the momentum of the outgoing particles, k1 and k2 are the momentum of the ingoing particles. How do I know that? Because of these exponents. Well, what are those Dirac deltas? k1 plus k2 minus k3 plus k4 times Dirac delta k3 minus k4 minus k5 minus k6. Well, the second Dirac delta tells me that k3 minus k4 should be equal to the k5 plus k6. Those are the external momenta. So this is actually Dirac delta to the 4, k1 plus k2 minus k5 minus k6, Dirac delta to the 4, k3 minus k4 minus k5 minus k6. So what do I have is this is nothing but the overall energy momentum conservation. K1 plus K2 is the momentum of the ingoing particles, K5 plus K6 is the momentum of the outgoing particles. So what I ended up having, M, this invariant matrix element that it remains after LSZ reduction. Or let me also introduce 2 pi to the 4 times Dirac delta to the 4 k1 plus k2 minus k5 minus k6 times m is equal to, well, all of these will be eliminated by the LSZ reduction. These two Dirac deltas, one of those are already outside. The other one is I can evaluate the K4 integral using one of those Dirac deltas, which will give me d cubed d4 k3 divided by 2 pi to the 4. Remember, one of these 2 pi to the 4s are already outside here. The other one will eliminate the 2 pi to the 4 in the k4 integral. And what will remain is 1 over k3 squared minus m squared plus I epsilon multiplied with, well, k4 from this integral, from that Dirac delta, k4 will be, or let me use this one, k4 will be k3 minus, let me say, kt, the total ingoing or the outgoing form momentum, squared minus m squared plus I epsilon. This will be the result of after the LS reduction. I wrote everything in momentum space. Well, how can I interpret this? You see, this was my bubble. What was K3? Well, K3 was the momentum corresponding to one of the Feynman propagators. Let's say this is my K3. Well, I can choose a direction for that K3, but replacing K3 with minus K3 doesn't really change anything. So choosing the direction of this momentum flow is kind of arbitrary. But with the conventions I have, remember, this is what comes. This is KT is arriving. K3 is leaving. What remains in the other propagator is, or let's say, what arrives is K3 minus KT. So K3 minus KT momentum arrives to this vertex. The KT momentum is also incoming into that vertex. And so K3 leaves that vertex. It comes over here. KT, this is also KT. KT leaves that vertex. What remains is K3 minus KT, whichever one you prefer. So what have we done? We draw the diagram. We assign momentum to all the ingoing. Well, the incoming particles already have their assigned momentum. Outgoing particles have their assigned momentum. For all internal particle lines, we assign also a momentum arbitrarily. But we also impose for momentum conservation at each vertex. So these Dirac deltas basically force momentum conservation at each vertex. At this vertex, you see this was K4. One of these Dirac deltas, this one, forces momentum conservation at this vertex, and this Dirac delta forces momentum conservation at the other vertex. I impose momentum conservation at each vertices, and then I integrate over all the internal momentum. So I could have started with K4 and K3, and then imposed the momentum conservation, or in defining my momentum, I could already just impose the momentum conservation. Some momenta will still be free. You see, even though if I impose momentum conservation here and here at both vertices, I cannot fix the value of K3. K3 is arbitrary. So I integrate over K3. There are these two so-called momentum space propagators for this line and also for this line, one having momentum K3, the other one having momentum K3 minus KT. I just multiply the momentum space propagators, integrate over all momenta that are not fixed by energy momentum conservation, and that is our invariant matrix element. since I impose momentum conservation at each vertex, I end up having an overall energy momentum conservation, that is this one. But when I factor that out, what remains is what I can use to calculate the scattering amplitude. So these are basically our so-called momentum space Fourier transform, Feynman rules. So these are the coordinate space Feynman rules. In momentum space, well, we again draw all connected diagrams contributing to the scattering. We should draw all of them. For each line connecting vertices include the momentum space propagator, which is 1 over just I over p squared minus m squared plus I epsilon. Multiply by lambda for each vertex. Divide by the symmetry factor, or calculate the factor explicitly. Impose momentum conservation at each vertex, so that not all momentum that you assign for each line connected vertices will have their independent momentum. They will be determined by other momenta. And if there are any momenta that are not determined by your external momenta, include an integral over that momentum. And that will just basically give you this expression straight away with, I should have I lambda squared over 2. I lambda is from each vertex, 2 is the symmetry factor. So again, just look at the diagram. Once you identify the diagram, look at the diagram, it's just, you can straight away write what your invariant matrix element is. For example, let's do an example. Within this theory, I can also write the contribution corresponding to this one. Well, let's see. This is K3, let's say. KT comes, so this is K3 plus KT. This is, let me call that K4. This will be K3, again from momentum conservation, because at this vertex over here, K4 leaves and at the same time it arrives, so there's no momentum change. And the corresponding contribution to my invariant matrix element, well, I have 1, 2, 3 vertices. I have I lambda cubed. Well, the symmetry factor is just 2. I cannot exchange out the upper line and the lower line. That's not a symmetry factor. I can only flip this upper bubble. That's my symmetry factor. And then I have I over K3 squared minus m squared plus I epsilon. Well, I have 2 of these.
Can't I flip the bigger loop?
No,
Can I loop?
if I flip them, the upper bubble becomes the lower bubble.
No, just vertical.
External legs are fixed.
All right.
Then I have I over K4 squared minus m squared plus I epsilon. It is the contribution from that loop. And I have, well, let me move it here. I have I over K3 plus KT squared minus m squared plus I epsilon. This is from this lower line. And I have some undetermined momenta, d for K3. K3 can take any value. K4 can take any value. So this is the corresponding contribution to my M for this, from this diagram. Okay, let me just, we will not be evaluating these integrals for the time being at least. And the main reason that we won't be evaluating them for the time being is that they diverge. They're infinite. Now look at this one. Let me look at the contributions that come from very large values of K4. Well, if K4 squared is very large, I can ignore the M squared. So for very large values, I will get contributions of this form. I can use spherical coordinates to evaluate these contributions. This is K4 squared when K4 goes to infinity. It is what we call a quadratic divergence. Well, if you look at this diagram over here, I have a similar divergence over there. You see, if I assume K3 is large enough, go to spherical coordinates from regions of K3, which is very large, I will get contributions of this form. K3 cubed dk3 divided by K3 to the 4, dk3 divided by K3, logarithm of K3 when K3 goes to infinity. From large regions of K3, there is a term which diverges logarithmically. So that's why we will not calculate these loops for the time being. We will, in most cases, either just write the expression and leave it there, or calculate tree-level diagrams where all the momenta are fixed, and so there are no momentum integrals. There won't be any divergences there. Now we will see what to do with these divergences later on. So there are ways of making sense out of all these infinite contributions. But we will discuss it shortly, probably towards the end of this semester. And in the next semester, we will, in QFT2 at least, there will be a long discussion about what to do with these divergences, because they, in general, appear in field theory computations.
So you have decided to give the QFT second QFT?
Well, you see, I still have 2 months to decide, so. Or to change my mind, even if I decide now.
What does it depend on, your decision to give QFT?
Let's finish this discussion, then we can continue. Any questions about what we had done before? Okay, there are still one more topic I would like to discuss on scalar field theory, but that will be after the exam. Well, Schwinger-Dyson series.